Welcome to the Exploratorium exhibit review. Today we will be looking at 3 different exhibits and explaining the physics behind each one of them. Our first exhibit has 3 parts. In each part there will be 2 ramps with a loop within them, and we will place a ball at the top of each ramp and it will slide down. On one ramp the ball will successfully complete the loop, and on the other ramp the ball will not. And we will explain why the ball is able to complete the loop on one but not the other. Let's get into our first ramp setup. So in the video we can clearly see that there are 2 ramps with different size loops in each one, and we see the ball complete the loop in the smaller loop, in the blue one, but is unable to complete the loop in the larger one, the pink one. So let's explain the physics behind this. In order to complete the loop, the centripetal force, which is mv squared over r, must be greater than or equal to the force of gravity, which is of course mg. That can be simplified to v is greater than or equal to the square root of g times r. R is obviously the radius of the circle. In the pink loop, we can see that is bigger and it therefore has a larger radius. So going back to our equation, if there's a larger radius, it needs a larger velocity in order to complete the loop. Since the ramps are the same and the balls are identical, they will have the same velocity going into the loop. But since the pink one has a larger radius, there isn't enough speed to complete the loop. Now let's go to our second ramp setup.
Wait.
From this video, we can see that the loops now have the same radius, but the lead up to the loop is now different. The pink loop has a steeper ramp than the blue one does. So as the ball travels down the pink ramp, it will pick up more speed because of the steepness of the ramp compared to the blue. Going back to our equation, we can see that velocity must be greater than the square root of g times r. In the pink loop, the ball has much more velocity, so it is able to complete the loop. But on the blue ramp, the ball simply doesn't have enough velocity to overcome the force of gravity and complete the loop. Now on to the third setup.
All right.
This setup was very similar to our first one, where the loops have different sizes. The pink loop has a very large radius, while the blue one has a much smaller radius. This time, they're not perfect circles though, as the blue ramp is, I don't even know what shape that is, more of a teardrop, more of an ellipse. But the physics is still the same. Since the blue ramp has a much smaller radius, the ball has enough speed to overcome the force of gravity, while in the pink ramp, the ball doesn't have enough speed, so it can't complete the loop. Now headed to our second exhibit, we will be looking at sound waves and seeing how different tube lengths will affect the pitch of the sound that is produced. In this exhibit, we will be exploring closed pipes, but it is good to know the difference between open and closed pipes. In an open pipe, Both ends are open, obviously, meaning that there will be antinodes at each end, which is where we'll have a maximum amplitude at the end. First, in a closed pipe, there's one closed end with a node and one open end where, again, we'll have an antinode. Since closed pipes have one node and one antinode, they will always have an odd harmonic. That means they can be first harmonic, third harmonic, fifth, and so on. Versus an open pipe, since it has two antinodes, can be even or odd harmonic. Now let's go take a look at our video and see how different tube lengths will affect the pitch of the sound. How many?
That's probably good.
As we just saw in the video, longer tubes produce much deeper sounds, while shorter tubes produce higher pitch sounds. This is because longer tubes will obviously have a longer wavelength, while shorter tubes have a shorter wavelength. And since wavelength and frequency are inversely proportional, a longer tube with a longer wavelength has a smaller frequency, while a short tube has a high frequency. High frequencies create high pitch noises, and low frequencies create low pitch noises. So therefore, the longer tubes will have a lower pitch, while a short tube has a higher pitch. This can be very easily shown with a trombone. As we can see, when he extends his arm, the tube gets longer and lower pitched sounds are produced. This is the same as the exhibit, as the longer tubes produce lower pitched sounds. And now for our final exhibit, we have a classic coin well. Wow! The coin well works because central pedal force causes the coin to circle the funnel, and gravity causes the coin to be pulled inwards towards the center. The coin spins faster as it nears the center of the funnel because of conservation of angular momentum. The coin well is also a good model of how our solar system works. Because the sun has so much mass, it actually can bend space-time, as you can see in this photo, which creates that funnel shape that we also have in the coin well. Gravity and centripetal force cause the planets to spin around the sun just like the coin does. Mercury orbits the sun faster than Earth does, and Earth orbits faster than Jupiter does. This is the same as the coin well, because the closer that the coin gets to the center, the faster it will orbit. The reason that the planets don't near the sun the way the coin goes to the center is that the sun is slowly losing its mass, which means that it has less gravitational pull, and the planets will slowly move away, actually, instead of moving in towards the sun. So that's my review of the 3 Exploratorium exhibits and the physics behind how they work. Thanks for watching. See ya.